All right, let's see. Yep, this is working, which is great. Morning, everyone. Welcome to week 4 of the PHYS1210 lectures. Just a reminder, because I know that sometimes it gets missed, but yeah, we have a class test this week. So that's on Friday, opens at 8 a.m, closes at midnight, and you've got about an hour. It's got the instructions on there from when you start the quiz to complete that. So there'll be 10 multiple choice questions, 2 long answer questions, both worth 10 points each. And there's a mock class test here, which resembles what you would expect for Friday. So you can try that as many times as you want before Friday and practice the upload of a PDF. So that's what you really need to work on to make sure that you don't get any issues during the test itself. So that's what that's there, not only to practice, but to make sure that you can upload the document. I also wanted to give a reminder, just based on what I've seen in the marks, that the pre-lab quizzes for the laboratories are actually worth a half a mark out of the 10. So it's quite a significant amount when you collectively put that together for your total 30%. So just make sure that you attempt that before the laboratory, and it's supposed to get you prepared for it as well, so that you're not coming in blind. Also, there are online options as well with online videos. So if you go into here and then go onto the resources tab, one of those links, it will take you to this page here, and it has heaps more information and also a video. So if you want to go in with a bit more preparation about what the equipment, how to use the equipment that you're using in that lab, you've got more videos here. So these are, if you couldn't make it due to COVID, you complete it online, but you can also just watch them to get more insight into the lab. And they only go for about 10 minutes, and you probably only want to watch the first few minutes to get the background. So yeah, I just wanted to point that out, because the laboratories are worth a lot of your final grade, and usually it's those types of the laboratories that make or break a grade, push you over or push you under. So we have our tutorial this week as well. So I've got my first set of tutorials this afternoon. Other than that, is there any questions regarding the content, class test, labs, anything? No? Usually it's not the ones that come to lectures that need to worry about this. It's more for the people listening online. But yeah, so let's make a start for today's lectures. So last week we were looking at kinematics, so motion that occurred over some sort of time period. And we looked at simple, horizontal, vertical, and then projectile, which contributed both. Today we're going to look at what happens when we apply a force and we get some sort of acceleration. And so this is based on Newton's laws. So we're going to be throwing back to Newton's first, second and third law. So if you've done high school physics, it's not going to be anything new. So we're going to look at what a force means. So we're going to introduce the equation mass times acceleration, and we're going to look at what to consider when something is static or not in motion, and when something is dynamic in motion, and how the vectors or the force vectors will change depending on what object we're looking at. So what I want you to start thinking about is, if you have something sitting on a table, for example, what force vectors might be acting on that object or on my hand. So for this bottle, for example, if I'm holding it stationary with no acceleration, I'm going to have a normal force acting up and a weight force acting down. Let me put my emails on silent before we move on. Must have forgotten to do that. In fact, I'll just close it. No, in my luck, I'll get another 20 emails during this lecture. So, all right. So that's what I want you to start thinking about in today's lecture, those force vectors. And it's going to be a nice follow-on from what we've already done. So, like I mentioned, we've already looked at kinematics in 1 dimension and 2 dimensions. We're not looking at 3 dimensions for this course. And we're going to look at more the dynamics. And so what happens when we're applying a force, pushing a phone across in the horizontal. We'll look at the Y forces as well. And again, we're going to start to look at vectors and applying those vectors. I've already mentioned that as well. But the reason I'm asking you to picture it is because you will need to do some free body diagrams, and that will make sense towards the end of the lecture. So we have some properties of forces, and it's one that I've already mentioned. So you've got the push, so you might push something across the floor, or you might pull it along with a string. So they're like action forces, I guess, but there are other sort of forces that we need to consider when we think of an object. And the one thing we do in physics is always simplify things. So this box could be a chair, could be anything, but we simplify it by just making the box the object that we're going to look at. And so we can get the push or the pull of the object, and we could get some acceleration. Or we might not get any acceleration. We might be pulling and it might be too heavy. And there's another force to consider when we have that sort of scenario. So we've got the 4 different types. We have the normal force. So that's the one that I mentioned when I had the bottle on my hand. So it's the opposite force acting on the weight of my bottle. And so that's always going to be perpendicular to the surface. So this is important when you start to do the free body diagrams. So if I tilt my hand on the side, it's going to be perpendicular to my hand, whereas the weight force is still going to be directly towards the earth. So, and that's what we'll have a look at. So first we're going to look at just an object sitting on a desk as an example, and then we're going to add more forces or more variables to that object. For example, we'll put it on a slant, so it might be on an incline, or it might have 2 objects in the system, and we'll have to add friction force eventually. But we won't add friction force today. That'll be in Wednesday's lecture. So you can see that it doesn't actually say, but if you have the force going across the screen for the friction force will go in the opposite direction. But like I said, we'll touch on that more in Wednesday's lecture. The other one we'll add is the tension force. So that's on a string, so we use inelastic string. We're not going to have any elasticity there to consider. We're going to simplify the scenario. And so the tension of that string used to pull the box is going to be towards the pulling direction. And so if we were to add friction to this, it would be going in the opposite direction along the surface or perpendicular with the surface. So we've got these types of vectors that we're going to start to introduce slowly, and then eventually you'll be able to do a complete free body diagram for any scenario that we have in front of us. So this comes on to drawing the vectors, which we already know how to do, but we're just going to make sure that we know for this scenario. So the vector for this one, if we have the tension force, if that's an inelastic string there, it's going to be going towards the pulling direction. But we have this angle of 30 degrees from the horizontal in the x direction, and we have the force. So we can sort of see that that's got x and y components. And we know that they're not easy to solve collectively, so we tend to separate them out. And that's what we're going to do. So we're going to use that. And so this brings us to the superposition of forces. So we just need to make sure that we draw the vectors in the right directions, whether that's vertical, horizontal, or both, and then we separate them out. And so that will come to this superposition of forces. So say this is the vector that I just showed, so it could be that, was it 30? Yep, 30 degrees from the horizontal, and it's got 10 Newton force. You would have to, that could be the sum of 2 different forces here. So we could have a string representing F1, we could have a string representing F2, both getting pulled in those directions, and collectively that would give us the R vector. So that's another scenario where you might be looking at. But I don't think we really get to that sort of complexity for these lectures. We more just look at the angles and the scenario that I just showed before. But if you did have this collective R vector, we could easily separate them out into the Y and X components. To do this, the first thing you want to do is you want to identify what direction is your positive X and what direction is your positive Y. So for this one, we've got the X and Y axes. They have the orientation like so. So we have the X axis and the Y axis. So I'm going to assume that the X axis is positive up the incline, but you could have it in the other way. It just means you have to change the signs. And there's not one direction that is right. It could be either is whatever you pick, and as long as it's consistent. So we have our positive x direction, positive y direction, and we have the total force vector pointing up towards, or the tension force up that string. And we can separate them out knowing the angle. And so we can get out Fx and Fy. So remembering that we have the normal force, so if we were to think about the other forces happening on this object, we would also have the normal force going up from the surface, and then we would also have a weight force going directly down towards the ground. And so for this example, if we had this force vector and then also the weight force, we would have two forces that we would need to put in the x and the y components, or separate them out. So we start simply, and then we'll go a little bit more difficult. And it's just using the simple trigonometry that we've already learnt last week, using similar to the initial velocity examples that we had. All right, so to find the components for this particular example, we're just going to use, for example, fx would be f cos theta, and fy f sine theta. Very similar to what we've already done last week. And to find the magnitude, I don't know where my magnitude lines are, it would be similar, it would be the square root of the squares of the sums of those. And we can also find the angle, if we didn't know the angle, that would be fy divided by fx. And that's just using the simple trigonometry that we've already covered. Again, just to remind us about the sum of the vectors as well. So if we were to consider this example here, we could find r by just adding all those vectors together. And I'll bring this up again because we'll be doing it a lot we'll be doing vectors and projectile motions in the laboratory this week. So we'll be basically shooting coconuts down from a tree, and we'll be drawing out all the vectors and learning everything we need to know about and in the tutorials, the different ways you can use vectors to multiply by scalar, the dot product and cross product. So get ready for that, just in preparation. All right, so on that, I think that's all the basics we need to know before we move on to applying them. We're going to start looking at Newton's first law, which is here, and then we're going to go to second law and third law. What you can see here is a skateboarder standing on a skateboard. If you draw force vectors, you will have one going down. This is the weight of the skateboarder, or mass times acceleration. There will be an opposing force upwards, which is a normal force, but we'll come back to that later. The skateboarder is not moving, and that is because there is no external force on it. Therefore, the acceleration is zero, and the velocity remains unchanged, or zero in that instance. When the sum of the forces equals zero, the acceleration equals zero, and velocity is constant. The tendency of an object to maintain its state of rest or uniform velocity is called inertia. So Newton's first law is also called the law of inertia. All right, so a very quick one, but that's a very simple concept that we use in physics. So if something's not in motion, for example, or there's no acceleration acting on that, then the sum of the forces equals zero. And we write that using the notation for sum, which is this. I can't remember which Greek alphabet letter that is. Anyone remember? Sigma, thank you. Yeah, so it's sigma, and then we got the force vector, so the sum of the forces all equal to zero. So they all cancel out. So that's what we're saying, that the normal force here is equal to the weight force. If I start to move that object up, the normal force is increasing in magnitude, so that it's no longer equal to zero. That's what we're saying. And we can use that. So if we know that an object is stationary, we can find the sum of the forces using those vectors that we've already identified or that we're going to identify, and we can use that to solve for perhaps the mass or something like that. So, and we can use that throughout. So the next one is going to be when we have something in motion. So that's using Newton's second law. Newton's second law states that the acceleration of an object is directly proportional to the net force acting on it, and inversely proportional to its mass. The direction of the acceleration is in the direction of the net force acting on the object. This can be demonstrated on a skateboard. When you have two people on the skateboard, you have an increased mass.
This means that the acceleration will be smaller. If you use the same net force to move a skateboard with one person, you will have an increase in acceleration in comparison to two people.
Alright, so this concept is not only used for force equals mass times acceleration, but any equation where we have direct proportionality. So from here, for the Newton's second law, we have something in motion. So all those force vectors do not equal zero, and there's some sort of acceleration associated with that. So for example, we could have a string attached to a box, and we're actually moving it across. So therefore we have some type of mass and some type of acceleration. The other thing to remember is that, so the direct proportionality. So if we have a mass and then we double that mass, the sum of the forces is going to be doubled as well. The same with the acceleration. So if we start to accelerate it more, the sum of the forces will equal twice that as well. And then we could also rearrange that to find the dependence of mass on force and acceleration as well. So you should be able to get those sort of relationships pretty easily from equations that we have in front of us. All right, and of course, from a throwback to last week's lecture, lecture 1, we can remember that the units is 1 Newton for force, but if we were to break that down into the base quantities, it would be 1 kilogram. So we must have the mass in kilograms, and then we must have the mass in metres per second per second. So I guess we need to identify something else that you would have learnt in high school physics if you did that as well. So the weight. So the weight and the mass of an object is different. So the weight is equivalent to the force due to gravity. So for that, we have a mass of an object in kilograms, and then we have the magnitude of the acceleration due to gravity, 9.8. And obviously the weight will depend, like the sign of the weight will depend on what you've identified as a positive y. So it's remember to know the difference between that. And so the weight force here is sometimes written as Fg or W. So that's you'll see those for different examples. Again, we've got G, it changes depending on where you are on the Earth, but we always use 9.8 or 9.81. So yeah, so it's important to remember that whenever it refers to weight in the question, for example, or the problem, that weight is a value that equals mass times G. So you can use that as part of the solution for when you start to look at the net forces. All right, so we have one last one, and this is going to help. We've already identified it, but it's going to help to draw those free body diagrams. So Newton's third law, and this is the last animation, don't worry.
Newton's third law states that whenever one object exerts a force on a second object, the second exerts an equal force in the opposite direction on the first. This can also be written as the force of the object 1 onto 2 is equal to the negative force of object 2 onto 1. If we go back to Newton's first law, you can see this when the skateboarder is standing stationary on the board. You have to remember that action and reaction forces act on different objects, for example, the foot and the skateboard. These are action-reaction pairs. So motion is possible because the force of action pushing laterally on the ground is balanced by the reaction force of the ground pushing on you. The two forces act on different things. It is important that you can identify these action-reaction pairs for the future problems that you'll come across. You'll need to be able to draw a free body diagram by identifying each of these action-reaction pairs.
All right, so for the skateboard example, we had two sets of action-reaction pairs. We had the one with the foot on the skateboard platform, and then we had the one with the, I guess if you wanted to make the skateboard a box, the weight of the skateboard on the ground and the ground pushing up. If you wanted to be more pedantic or more accurate, you can consider the wheels. But we're not up to rotational motion, that's next week? Yeah, next week. I just had a complete blank. So we'll be looking at how what forces are acting on the wheel next week, but not this week. All right, so we have the action-reaction pairs. We need to be able to draw those vectors that represent those action-reaction pairs. And they're not always equal and opposite. Sometimes we'll get a little bit more to make it go into motion. But in fact, if you just think of the simple act of walking across the surface, like I constantly pace up and down here, that in itself has those action-reaction pairs. So you start moving forward, you push backward on the ground with your foot, and this allows you to get that acceleration across the floor. But it's not always as easy. So with that skateboard, there was more than one action-reaction pair. But when we consider a problem, such as this one, we have a block, a big block, could be a wardrobe, let's call it a wardrobe to make it a little bit more interesting, and then we have someone pulling on a string perhaps. So we have to consider those two objects separately to solve the problem. So for the block and the rope, we have friction force. Now we haven't covered that yet, but we will on Wednesday. But we'll have those two forces acting on that wardrobe. Then the mason will have two forces acting on them. So we separate them out, find the net force on the wardrobe, the net force on the mason, and this will allow us to solve the problem. And we'll see how to do that Wednesday. But yeah, so we need to separate them out, write the forces vectors on there, or the free body diagram for each object, and then we can find the net force. So if it's stationary, so if there's no motion of the wardrobe or the mason, then we use Newton's first law where the net forces equal 0. If there is some sort of acceleration, then we use the net forces equals mass times acceleration. All right, and then sometimes they might be accelerating at the same acceleration, both the wardrobe and the mason. So we can use both sets of equations for the net force, rearrange and find an expression for acceleration, and we can solve it. So getting a bit of ahead of myself, but the most important thing that will be really helpful, especially if you're a visual person, is to draw that free body diagram. And so that's what we've got here. So we have different ones. We've got a basketball a scenario or a runner. And I guess it's just knowing, so we have the weight force going towards the earth, and then we have the force of the block on the runner. So we can separate that one out into the X and Y components. This is just a single free body diagram for that application. Again, we have this one where someone is off the ground jumping to dunk the ball. And so for that scenario, we've only got the weight force, mass times acceleration, because he's not touching anything else. And then we've got this one where he's standing blocking, or whatever they do in basketball. And we have the weight force and the normal force that are opposite in direction because it's in the Y components. So I guess we have the free body diagram scenario. I think I found this off a paper somewhere. I can't remember. I couldn't find the reference. I left that off. But yeah, so this is another free body diagram. I just thought it was quite funny. But anyway, and that's a pretty quick lecture for today. I'm going to go through the questions though because we have got time. So what we're going to do next, so now we've got the fundamentals, we know how to draw the free body diagrams, and now we're going to start applying it to problems to solve, for example, for perhaps the acceleration or the tension force, anything like that. But let's go through some questions just to make sure we're all on board. So we have a book which is lying at rest on a table. The book will remain there at rest because A, there is no net force, but the book has too much inertia. B, there are no forces acting on the book. C, there is no net force in the book. Or D, there is a net force, but the book is too heavy to move. So which one is that? Hopefully it's pretty obvious because you've been here for the lecture. C, thank you. Too easy. That's good. So that's C. And that one's pretty straightforward. So the forces are acting on the book, but only in the Y direction, normal force, weight force, just like we've said throughout the lecture many times. All right, so what about this? When standing on a bus pulling up to a stop, you tend to need to hold on to support. So identify the forces acting on you as the driver applies the brakes. So this one needs a little bit more thought, and we've sort of covered it in a little bit of the lecture today. So is it A, the force of the floor holding up your feet, gravity acting downwards, the force of the bus stopping and gravity, or the force of the brakes and gravity, or the conservation of momentum. Hopefully you realise we haven't covered that one yet. So which one do we think it is? A? Yep, that's good. Yeah, so it's the force of the floor holding your feet up and gravity acting downwards. Yes, we have that pull from the brakes, but if it's just looking at you as a single object, then they're the two forces. All right, this one's a bit more to do with Newton's second law. So we have constant force, and it's exerted on a cart that is initially at rest on an air track. Friction between the cart and the track is negligible, and the force acts for a short time interval and gives the cart a certain final speed. So we have no friction to consider, and we haven't covered that yet anyway. So to reach the same final speed with a force that is only half as big, the force must be exerted on the cart for a time interval, which is A, 4 times as long as a stronger force, B, twice as long as a stronger force, C, half as long as a stronger force, or D, a quarter of that of the stronger force. So you might need to consider something from last week to help you with this one. I'll let you have a think about it. Sorry? Yeah? Yeah, that's right. Yep. So it should be B. And I've got here, so half the force is half the acceleration. So this means twice the time is needed to get the same velocity. And that's just based on what we learnt last week in kinematics as well. So it's applying both weeks. All right, how many we got left? We'll just do one more. So what can you say about the force of gravity acting on a stone or feather? So again, this is distinguishing the difference between weight and mass. So is it AFG is greater on this feather? And I guess it's assuming that they're not the same weight. Just making, yeah. All right, BFG is greater on the stone, or the force due to gravity is 0 on both due to vacuum, which is not the case. And DFG is equal on both, always. So which one do you reckon it is? B, yep. And it's assuming that the stone is heavier. I mean, you could have a really small stone and a really big feather, but it should be that one. All right, so it's a relatively quick lecture, and I guess that's just to make sure there's no questions about the class test this week. You can come up and ask me anything. And yeah, I guess that's it. I'll see you at the tutorials this week, and let me know if there's anything else I can help with.